We have shown that if y1 and y2 are solutions to the differential equation y double prime plus p of ty prime plus q of ty equals 0, and the Wronskian of y1 and y2 at a value t naught is non-zero, then the general solution of the differential equation is the linear combination of y1 and y2, y equals c1 times y1 of t plus c2 times y2 of t. Now, this relies on evaluating the Wronskian at y1 and y2 at a value t equals t naught. So a question to consider is, does it matter which value t equals t naught we choose to evaluate the Wronskian at? For homogeneous second-order differential equations with constant coefficients of the form ay double prime plus by prime plus cy equals 0, with r1 and r2 the solutions of the characteristic polynomial, we found that the condition only depends on r1 and r2. In particular, we found that the Wronskian of e to the r1t, e to the r2t not being equal to 0 happened if and only if r1 and r2 were distinct values. They were not equal to each other. So in this case, it did not depend on which value t equals t naught we evaluated the Wronskian. But what about in other cases? Abel's theorem shows that whether or not the Wronskian is equal to 0 is independent of t naught for linear homogeneous second-order differential equations. In particular, Abel's theorem says that if y1 and y2 are solutions to the differential equation y double prime plus p of ty prime plus q of ty equals 0, with p of t and q of t continuous on an open interval from alpha to beta, then the Wronskian of y1, y2 of t is equal to a constant c times e to the negative integral of p of t dt, where the constant c here depends on y1 and y2, but is independent of t. So since e to some power can never be equal to 0, we can see that the Wronskian at y1 and y2 is equal to 0 if and only if that constant c is equal to 0, which is independent of t and only depends on the functions y1 and y2. So in general, whether or not the Wronskian is equal to 0 is independent of which value t equals t naught we choose. To prove Abel's theorem, we'll start out by using that y1 and y2 are solutions to the differential equation. So we know that y1 double prime plus p of t y1 prime plus q of t times y1 equals 0, and we know that y2 double prime plus p of t y2 prime plus q of t times y2 equals 0, since they're both solutions to that differential equation. Now, we can eliminate the last term by multiplying the top equation by y2 and the bottom equation by y1 and subtracting the top from the bottom to get y2 double prime times y1 minus y1 double prime times y2 plus p of t times y2 prime times y1 minus y1 prime times y2 is all equal to 0. And we can write this equation in terms of the Wronskian y1 times y2 prime minus y2 times y1 prime by computing the Wronskian's derivative. In particular, the derivative of the Wronskian is the derivative of y1 y2 prime minus y2 y1 prime. We can do this term by term using the product rule. The derivative of y1 times y2 prime will be y1 prime times y2 prime plus y1 times y2 double prime. And the derivative of y2 y1 prime will be y2 prime times y1 prime plus y2 times y1 double prime. And we're subtracting this term from the first. Once we've done this, we can see that the terms y1 prime times y2 prime minus y2 prime times y1 prime cancel, leaving us with the derivative of the Wronskian being y1 times y2 double prime minus y2 times y1 double prime. So our equation becomes a first-order linear differential equation of W. In particular, our equation above can be written as W prime plus P of t times W equals 0. This is both a linear and a separable differential equation in W. Rearranging this equation as W prime equals negative P of t times W, we can solve for W as a separable differential equation, which gives the condition that the Wronskian is equal to c times e to the negative integral of P of t dt, the conclusion we sought to find in this proof for Abel's theorem.